In this lecture, we're going to talk a little bit about inertness and lability of coordination compounds and discuss the mechanisms of oxidation-reduction reactions. First, we need to explain the difference between labile and inert complexes. In this part, I will remind you that labile is a kinetic term that describes complexes with half-lives less than 1 minute. That means when they are in a reaction, they are used to a great extent within 1 minute. Inert compounds are complexes with half-lives greater than 1 minute, so the reaction proceeds very slowly. The factors that influence how labile a complex is related to the strength of the metal-ligand bond. Here are the factors that affect lability. Labile complexes have small charge densities and small activation energies. The complexes contain bulky ligands and have small overall charges. They also have very weak metal-ligand bonds. Inert complexes have large charge densities and large activation energies. They generally contain small ligands, and the metal cations generally have an overall very large positive charge. They also form very strong metal-ligand bonds. Two questions can be asked based upon this information. First, it has been observed that second and third row transition metal complexes are generally inert. Why is that? Second, why are Cr3+ and low-spin CO3+ complexes inert? So let's answer the first question. Why are second and third row transition metal complexes inert? Well, it's because they have large 4d and 5d orbitals that can form very strong sigma bonds with the ligand's molecular orbitals. This leads to very strong sigma bonding and therefore inert compounds. So the bigger the d orbitals, the more they can overlap with the ligand's molecular orbitals and form very strong bonds. Now that's an easy question to answer. Why do fourth and fifth row transition metal complexes form inert compounds? However, it's also been observed experimentally that Cr3+ and low-spin CO3+ forms inert complexes as well. So, why? Most first-row transition metal complexes are labile. Cr3+ and CO3+ complexes are almost always inert. The change in the crystal field stabilization energy when going from octahedral coordination to a 5-coordinate transition state will help us explain why these cations are inert. So we will be looking at the change in the crystal field stabilization energy when going from octahedral coordination to a square pyramidal intermediate. When this happens, when you look at the change in crystal field stabilization energy between these two geometries, if the formation of a 5-coordinate transition state is favored, the octahedral compound is labile, and the change in CFSE should be positive. When there's a negative change in CFSE, that means the formation of a 5-coordinate transition state is not favored, and the octahedral compound is inert. Let's look at some data to support this. This table shows the difference in crystal field stabilization energy for cations with different d electron counts. If we look at chromium 3+, it has a d electron count of D3. The difference between the octahedral crystal field stabilization energy and the square pyramidal one is negative 0.20. That means that this is an inert complex when you form complexes with Cr3+. V2+ also shows the same inertness. CO3+ is a D6 metal cation, and if you take the difference between the octahedral field and square pyramidal field when looking at a low spin complex, the difference in their crystal field stabilization energies is negative 0.40. This is a low spin complex. Nickel 2+ in the D8 state will also show this, giving a negative change in the crystal field stabilization energy. So now that we've talked a little bit about the difference between labile compounds and inert compounds, let's focus on oxidation-reduction reactions and the mechanism behind them. Oxidation-reduction reactions, remember, they are electron transfer reactions. There are two possible mechanism types for oxidation-reduction reactions: outer sphere and inner sphere. The mechanisms for oxidation-reduction reactions were determined by Henry Taube, the same person that determined that compounds were either labile or inert. He did this work in the 1950s, and he won a Nobel Prize for his work in 1983. There are two types of electron transfer mechanisms. We'll look at the outer sphere mechanism first. In the outer sphere electron transfer mechanism, an electron is transferred from one metal cation to another, but no bonds are formed or broken really. It's an electron hop from one coordination compound to another. This is typically observed in self-exchange reactions. Reactions where two nearly identical chemical species transfers an electron. The only difference between the two complexes is the oxidation state of the metal cation. So let's look at an example of this. In this reaction, we have Ru H2O6 2+ reacting with Ru H2O6, but the water is radio-labeled, that's what the star means, 3+. An electron is transferred from the Ru H2O6 2+ to the Ru H2O star 6 3+, forming these two compounds. Notice that no ligands are exchanged. All 6 of the ligands on the original ruthenium compound are still just plain water, and all 6 waters on this part of this complex are still radio-labeled. When this reaction occurs, the rate constant is 44 reciprocal molar reciprocal seconds. This is a fast reaction. Why doesn't ligand exchange occur? It's because that the reaction must occur between two substitutionally inert compounds. So for example, the rate constant for this compound, Ru H2O6 2+, is 10 to the minus third per second. This is classified as an inert compound.